In last class, we have discussed about the commutation problems in the DC machines, and we came to know that armature reaction and LdI by dt voltages are the two main problems associated with the commutation. And in armature reaction has two effects. One is the magnetic neutral axis shift and the flux weakening effects, right? And LDI by dt voltages are due to change in the coil position from one pole to one pole. Okay, so these two, magnetic neutral axis shift and LDI by dt, are going to cause the sparking at the brushes, and the flux weakening indirectly reduces the EMF induced in the generator. Okay, now here I would like to mention or highlight or make a note that this commutation problem is not common to a DC generator, but it exists in both the generator as well as the motors, DC motors. Okay, I am repeating, commutation problems are common in both generators as well as motors, right? So I have shown two diagrams here: DC generator, DC motor. Generator, here the rotor is actually coupled to a prime mover. This is a prime mover, so which is actually driving this rotor of a generator, and which in turn, linking the magnetic flux produced by the main poles, will generate the EMF at the terminals of the brushes, which we can now connect to any electrical load. Okay, so in generator, the mechanical power supplied to the machine is converted to the electrical power output, and in opposition to this, in a DC motor, actually we will be feeding the armature through a DC voltage or DC power supply. We are feeding the armature of the DC motor through a electric power supply, DC electric power supply, and due to this, the torque will be produced and it rotates. I'll again, when I come back to DC motors, how the torque developed in the machine and derivation to that I will be explaining, but for the time being, you assume that the torque is developed and it will be rotating, and this is coupled to the load. Okay, this will be indirectly driving the load. This is mechanical load, right? So here in generator, the power flow is from this side, and in motor the power flow is from this side. And when it comes to armature reaction, as we have discussed, the effect of the flux produced by the armature currents is causing the distortion in the main flux, right? So in case of generator, the current direction in the coil sides, under north pole and south pole is as follows, like this. Under north pole we have dots like this. Dot means the current, the EMF is in this direction, it is coming out of the page, right? And cross means it is going inside, like this. So it is plus minus this side, and this is plus minus this side, like this. Okay, so in case of generator, these are the current directions, and with these current directions in the armature coils, now we are going to have the shift in magnetic neutral axis towards the direction of the rotation. shift in magnetic neutral axis towards the direction of rotation. Okay, you have to keep this in mind, right? But whereas when it comes to a DC motor, as we are giving or we are feeding the current into the armature, now plus sign indicates the current is now into the brushes like this. Here in this case, plus sign in generator, plus sign indicates the current is collected from the brushes like this. Now I am feeding here in motor, I am feeding the current into the motor like this. Now the current direction in the armature conductors under north pole now will be cross like this. In this side it will be cross, and under south pole it will be dot. Okay, so this is directing like this. Now due to this currents in the armature coils, now the armature reaction try to distort the magnetic neutral axis reverse to that of the rotor movement. Okay, it will fall back. Okay, so neutral axis now shifts back. This is rotating speed of the armature, and neutral axis is now falling back. Okay, so you have to understand how the armature reaction exists both in generator as well as motor. But in generator the shift is towards the rotation, and in motor the shift is against the rotation. Okay, now, and I said in case of generator the armature reaction has the effect of flux weakening. Flux weakening indirectly, as the flux reduces, the induced EMF also reduces. This is in case of generator. Now in case of motor, here also the flux weakening takes place, but as it is a motor, the net amount of torque developed by the motor also reduces, because I will come to this derivation later classes. The torque is proportional to same constant K multiplied by phi into the current, armature current. This is armature current. Okay, because armature current is fixed, and now the flux is reduced, the torque, overall torque developed by the motor reduces. Okay, this is in case of motor, right? So commutation. Now coming to the LdI by dt voltages, LdI by dt voltages also exist in both generator as well as motor, because as this coil initially it was here somewhere, at some moment it is coming to neutral axis and then it is moving to this side. So the coil is coming from under the influence of south pole to north pole. So earlier it was having a direction, current direction like this. Now it has to, now under north pole it has to change its direction. So from this direction to this direction, this is going to happen at the neutral axis. So this takes place within a fraction of times, because as the rotor is rotating, the commutator segment, the brush collecting from that segment is very short span, so the current reversal will develop these voltages, LdI by dt voltages. Okay, so similar type of effect will be noticing in case of motor as well. So these problems are common to generators as well as motors. Okay, so keep in mind that I am not only talking with respect to generators. This armature reaction and its problems are associated with motors as well as generators. Now let us talk about how to mitigate these commutation problems. What are the ways employed in practice to mitigate the commutation problems? The first and foremost is the manual adjustment of brush positions on the commuted segments. Okay, so what do you mean by this? As the suppose if in this diagram the dotted line is the normal magnetic neutral axis without any load on the generator, but as the loading on the generator increases, this magnetic neutral axis shifts to this one. And let us assume that this magnetic neutral axis is pertain to a full load condition. Okay, and in intermediate loading condition, it will be somewhere in between these two magnetic neutral axes, right? Now we have to check, depending upon the load, the brush position should also be shifted from one position to one position from time to time. Now that is how the olden days, very olden days, this method is employed. But what are the main problems with this method? It needs to be adjusted the brush positions based on the loading conditions, and which is practically impossible. Keep on changing the brush positions is very impracticable. Okay, and that is why this method is absolute by the end of year 1910. So this was initially implemented, but it is gone absolute by the year 1910. And suppose if we genuinely or judiciously keep the brush position fixed at one loading condition, then the sparking takes place at other loading conditions. Suppose if the duty cycle or the duty cycle of the generator is having maximum duration for one particular condition, that is 3/4 load. At 3/4 load, maximum loading that generator will be occupying, and very little time it will be at no load, or it may be full load. Okay, so I try to keep my brushes at 3/4 load position, fix my brushes at 3/4 load position, but at other times when it is either no load or it may be full load, then under that condition the sparking takes place. So this is also a problem. So that is why this method gone absolute. Now second method is a commutating or interpole placement. The principal objective is to induce equal and opposite EMF in the coils undergoing the commutation process, right? So now due to this magnetic neutral axis shift, now this coil and this coil, actually it should be 0, but now having some EMF induced in these two coils. Now if I try to induce in these coils a opposite EMF like this, same coil, due to this interpole flux, if I try to induce the opposite EMF, this is cross and this is dot here. If this is a dot, then I will be trying to induce a cross here. So that ensures that the total EMF will be cancelling and there is no EMF induced in the coil like this. Now for this, what I have to do? So I have to place an interpole like this. In addition to the main poles, I have to place a interpole between two pair of poles like this. So one interpole exists between two pair of poles. So if I have two poles, then two interpoles like this. If I have four poles, then four interpoles will be there. 1, 2, 3, 4 main poles, north, south. Then I will be having one interpole here, one interpole here, one interpole here, and one interpole here, like this, right? Now, these interpoles are connected in series with the armature current to make into account the change in the loading condition, because as the loading on the armature goes on changes, then the actual EMF induced in this coil will be varying. Now I can't fix this MMF in this interpole to a fixed value and keep on inducing same amount of opposite EMFs at all times, but it has to change according to the EMF present in this commutating coil. So for that I have to place these coils in series with the armature coils. So how do I connect? So I will be joining the interpole windings like this. So this will come and it will connect the other interpole, and this will go at the end to the other pole here. Okay, so now if you notice, what is that? To accommodate the load changing, I have to connect this interpole winding in series with the armature. You keep this in mind. Okay, right. Now in what direction? Next question is, in what direction should this interpole is a north pole or a south pole? How should I come to a conclusion? See, because in generator magnetic neutral axis is shifting towards the rotation. Now the south pole influenced coils will be coming to here. This is cross. Okay, this is actually a cross here. So I have to induce a dot EMF. Now dot EMFs are induced under north poles, like here. Is it right? Now similarly, this coil actually because of this magnetic neutral axis shift, it is having a dot here. Now I need to induce a cross EMF into this coil. Now cross EMFs are induced under the poles having nature of south pole, right? So I will be connecting these interpole connections such that a north pole is generated ahead of this north pole, and a south pole is generated ahead of this south pole. Because I am rotating the direction, rotation is like this, so this will be a north pole before the north pole, south pole before a south pole, like this. Are you followed? But this is in case of generator, but in case of motor it will be reverse. Now because the magnetic neutral axis is shifted backside, now this dot will be coming here, and I have to induce a cross here. So cross means this is a south pole, and here it is shifted back, so this is cross, so cross will come here. Now I have to induce a dot, so dot means this is a north pole, so it will be reverse to that of generator. Motors will have interpoles with signs of pole, it will be opposite to that of a generator. Are you followed? Right. Now interpoles, okay, I have now told about the how to accommodate with the load changes and how they are connected in generator as well as motor. Now the question is, how effective these interpoles are doing their work. Now interpoles can address to the problems arising due to shift in magnetic neutral axis and LDI by dt problems, but not the flux weakening. The flux weakening still exists even after placement of interpole. Okay, so with interpoles placement, I can eliminate to maximum extent the magnetic neutral axis shift and LDI by dt voltages, but there is still the flux weakening or torque reduction problems are still exist in generators and in motors respectively. Okay, so for that we have to think some other alternative. So that is why interpole are employed mainly in a moderate size DC machine, So in case of large DC machines, either generator or motors, the flux weakening and the reduction in torque is significant in nature. We cannot allow the generator to reduce its EMF, or we cannot allow the motor to reduce its torque develop. So because these terms are significant in nature, we have to think some other alternative. Okay, the next method is a compensating winding. Now I'll keep asking you some questions here. Now, how many turns should I place on the interpole? You think over about this for a while. How many turns I am shown here the turns here like this. Now how many turns should I place here? Because current is fixed. Ni is the MMF. Current is same as that of armature. Then I don't have any control on that current, but I have control on the number of turns. So how should I come to that number? So think over. I'll come back to that point. Next method is the compensating windings. Now here these compensating windings are placed in the pole shoes. Here I have shown this figure. First figure is normal machine, DC machine. Okay, so in first figure I have shown the normal DC machine with the main poles and the armature and its slots accommodating the armature coils. And now the main flux distribution is normal as usual. It is right. This is normal flux distribution in the machine, right? The flux density across the pole face is constant. This is I'll come back to this point later. The flux density across the pole face is constant in this case. But now when I come to the second picture, due to the currents flowing in the armature coils, the flux now distorts and it weakens at this end, and this is trailing end and this is leading end, and the flux is becoming stronger at the leading edge. Okay, now due to this effect, the magnetic motive force MMF due to fields, now earlier it is like this, the fields are flowing like this, flux lines are flowing like this, and now they will be flowing like this. Now due to this, the magnetic neutral axis is shifted, MNA, right? Now this is combined effect of main flux as well as armature flux. Now coming to third figure, the compensating windings are placed at the pole faces. Here we have slots here at the pole faces, and these pole faces, these slots will accommodate windings like this, and the current flowing through these windings will be opposite to that of the current flowing under the coils under this pole. Okay, so this is north pole and these coils are under the north pole. So whatever the current direction is there in these coils, the current direction is opposite in the compensating windings. It is cross here. I hope you have understood. And when it comes to the south pole, the coils under the south pole is having a cross direction here, and the compensating winding will now have the current directions dots. Okay, now what happens is the flux due to these compensating winding try to oppose the main oppose the flux due to the armature field, right? This red color flux is due to the armature currents, and the blue color field is due to the compensating windings. Now if we try to adjust the mmf of the field compensating windings, then we can totally eliminate the armature reaction from the machine. Okay, are you followed? The compensating windings are placed in the slots of the pole shoes, and how they are conducting opposite to that of the armature currents that are exactly under this pole. Okay, so now this is the cumulative effect of main flux, armature flux and compensating flux. Now the due to the nullification, now the flux in the rotor will be as usual, like this, as that of in the first case. Okay, so now what we can conclude from these discussions: a compensating windings are placed in series with the armature winding, so that to take account the load changes. The mmf of the compensating winding also changes with the change in the loads. Okay, because it has to completely nullify the armature reaction. And mmf due to compensating windings is equal and opposite to that of the mmf due to rotor currents at every point under the pole faces. That is what I have said. The only disadvantage with this is that they are expensive in nature. These compensating winding are expensive because we need to have slotting of the pole faces, accommodating the coils in the pole faces, and they have to carry the same current as that of the armature current. So the thickness of the compensating winding is equal to that of the armature conductors. So it is normally very, very expensive in nature. Now machine using compensating windings should also have interpoles. Listen, machines using compensating windings should also have interpoles. So if I use compensating windings, then I have to use also the interpoles. Since the compensating windings do not cancel LdI/dt voltages, it actually completely eliminates armature reaction, that is shift in magnetic axes, neutral axes, and the flux weakening. These two are addressed, but not LdI/dt with this compensating winding. So to address this, I have to place the interpoles along with the compensating winding. But what is the other advantage is that, however, the interpoles do not have to be so strong. Earlier in previous case, the interpoles, it has to be addressing the magnetic neutral axis effects as well as LdI/dt effects. But in case of placement of compensating winding, I no need to now bother about the magnetic neutral axis shift, but only talk about the LdI/dt effects. So the interpoles will be not so strong, because now the effects of magnetic neutral axis shift are not present in this case because of use of compensating winding. Is addressing that MNA shift, right? Now due to this economical aspect, costly, and then this type of compensating windings are employed in heavy duty DC machines. Normally they are employed for heavy duty DC machines, both in generators as well as motors. So again, I will ask the same question at the end: how many turns I have to use? How many turns I have to use in compensating winding? Right? So for this, you have to understand the basic principles about the magnetic production. Let me discuss about them. These are, I think you have studied in +2, or you will be studying again in electromagnetic field theory, much about this, and also about in circuits also. Okay. Uh, Now magnetic fields, I am talking about magnetic fields. How they are produced. So if I straight away take an example and then explain. So this is a core, okay, like this. Now I place a coil of N turns and supplying current I. Now this will set up flux in the core. This will set up flux in the core like this, right? And the principle behind this is the Ampere's law. In electromagnetic field theory, you will be coming across this Ampere's circuital law, that is closed integral of H dot dl is equals to I enclosed, I or I net. Okay, H is a vector and dl are the vector, right? You may have come across this one. So if I take the closed integral of this one under any plane like this is on any plane. So dl H dot dl, these are two vectors, taking the dot product and summing all the summations, that will lead to the final current enclosed in this conductor. Now similarly here, what is happening, right? So there are so many turns. So if I see here the cross section, this so many currents are there here, and the flux is now enclosing, right? So I net, this is equals to I net is equals to simply H dot H into dl, H into L. dl is now, okay, I'll write down one point here. All the magnetic field produced by the current will remain inside the core, because the permeability of this core is very, very high than the permeability of the air. That is why the flux is confined to the core, right? So the path of integration, of the closed loop is say the mean length of the core. The mean length of the core means this length, mean length of the core, LC, right? So the intensity, field intensity multiplied by mean length is equals to I net. I net is actually, now this flux is cutting the current in each turn multiplied by n turns. So that is actually n into I, right? So H is equals to this n into I divided by LC. This n into I is actually the MMF, magnetomotive force of the force driving or generating this flux. Okay, so this is H, actually what you say is MMF, ampere turns per meter, right? Now I can say this H is the driving force. I can say this is a driving force behind the production of the flux in the core per unit length, and then the relation between the magnetic flux density and H is mu. The permeability of the material, that core material, multiplied by the intensity gives me the flux density in the core, right? And also what is B? Now what is this mu? Mu is the permeability of the core, and which is actually the relative, I can say mr multiplied by m naught, permeability of the air multiplied by the relative permeability is equals to the actual permeability, or otherwise relative permeability is equals to mu by mu naught. Mu is the permeability of core, right? And this is permeability of free air, right? And also the flux density is B is equals to flux per unit area, or mathematical I can say the flux in the core is the B dot dA, this surface integral of B dot dA. So I can say this is core like this, so it is having the flux directions coming out like this. So this area normal is again along the flux direction, and the normal vector of this plane surface area is also along this. So the dot product is maximum, so it is just the product of B into A. These are scalars, these are vectors. So I can, in textbooks it will be bold in nature, but I can't draw here. Now these are scalars, scalar quantities. So flux density, magnitude, and area of cross section, right? So I can say that this flux is equals to B into A, which is equals to B is mu H into A, and H again I can write in terms of this one, N I by LC into A, N I LC into A. This is flux in the core, right? So in other words, this can be analogously can be treated like this as a equivalent electrical circuit. So we have electrical circuit this is V voltage, this is R resistance, and the current flowing through the circuit is I, and the relation is I is equals to V by R. This is electrical circuit, right? Analogous representation of this magnetic circuit equivalent to this electrical circuit can also be represented like this. Now whereas this driving force will be the MMF, that is MMF R, which is Ni, this is F, and this is, instead of resistance, now it is a reluctance of magnetic path. And what is this? This is, instead of current, it is now flux. So flux is equals to MMF F by R, where F is Ni, and here from this I can write down here flux is equals to Ni by Lc divided by A into mu. Now this R is, now this reluctance R is Lc divided by A into mu. Okay, so now I can change the flux in the core by changing the number of turns, or by changing the current passing through the coil, or I can also change this flux by controlling the length of the core or the cross section of the core, or I can change a material of different permeability. So these many parameters are there which I can control the flux, or indirectly the flux density in the core. Okay, now let me show the equivalent circuit also. For suppose in a machine, if it is having a 4-pole, so let me draw the core, rotor. Now this is one pole, this is another pole, this is another pole. North, south, right? Now if you notice, I will draw only one flux lines. So this flux line is entering into the core, and this is going into south pole, and this will close like this. Similarly here also the flux line coming out, it goes into the south pole and it enters into the north pole like this again. Similarly some flux lines entering into the, coming out from the north pole, it will enter into the south pole, again it goes back into the north pole like this. So this is, now some flux lines coming out from this north pole will go into the south pole and come and close like this, right? So these are how the flux distribution in the stator core, poles, pole shoes, air gap, rotor, and it is going back like this. So this flux is having so many paths. Earlier I have shown single core like this. This flux is flowing in single core. Now what is happening here? There are so many mediums, right? Let me draw that. So for example, this core, I am taking this flux. This flux is having stator core like this. This part, let me assume that this is a stator core, and this part, let me assume this part, and this part, let me assume pole core, this part and this part, and then it is having some pole shoes. let me assume this part is pole shoe core, and now it will enter into the air gap. This is air gap. Then it comes, suppose this is coming like this flux. So stator, it is starting from stator, core, pole shoes, then entering into the air gap, then entering into the rotor, then again entering into the air gap, then pole shoes and poles, and then it is closing like this. So in case of calculating the reluctance, you have to calculate the reluctance of this path, 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 like that, right? So I mean to say that now here, as simple as the relations holds good for electrical circuits, the same type of relations holds good in magnetic circuits also. For example, if two resistors are in series, R1 and R2, their equivalent resistance will be R1 plus R2. Now similarly, if two mediums is having different reluctances R1 and R2, then the overall reluctance of this medium from here to here will be R1 plus R2, like that. If it is having a parallel combination R1 and R2 and R3, then the parallel combination 1 by R equivalent is equals to 1 by R1 plus 1 by R2 plus 1 by R3, right? If the flux is allowed to flow through different mediums like this, then the reluctance at this point will be the same parallel combination of all the three reluctances. So same principles holds good in magnetic circuits also, right? So now let me draw the equivalent circuit, electrical equivalent circuit of this one. Okay, so how can I draw? Now there are coils here, which are the driving forces, N into I, like that. So I am taking one loop. So there are driving forces. This is south pole means up. Then there is a north pole here, it is plus sign this one, and this is north pole, and this is south pole, right? Now now there is pole reluctance, then there is pole shoe reluctance, this is pole shoe reluctance, then there is reluctance due to air gap, then there is reluctance due to core. Now same type of, this is, we have core, then we have RAG, then we have R pole shoe, then south pole MMF, then we have again RP, and then we have RS. I hope you have understood, right? So the similar type of, this is RS. So similarly I can draw all the four directions. So three resistances are there here, reluctances are there, and one reluctance here. So three reluctances and one reluctance here, like this. So flux distribution is like this. So you can find out the flux any position in the core. Only thing is you need to simple equations. You write down the simple equations, and then you can find out the strength. Flux is, because flux will be constant from here to here. So from here to here, again it's constant. From here to here it is constant. but there may be varying flux densities depending upon the reluctances and the cross section. So you can find out these reluctances for various sections through using this formula. R is equals to LC by A mu. So length of that magnetic core and the cross section and the permeability. So for each section you can find out the reluctances, and then you can find out the various flux densities occupying in the machine, right? Now, so knowing all this, now I am coming back to how do I place the number of turns. Here, so here in interpoles, so I have to decide the number of turns. So how do I decide? I don't have control on I. This is same I am flowing through I am allowing the armature current through this coil, right? So current is varying according to the armature loading. Now I have to fix the MMF. Now we have to first estimate what is the voltage actually inducing in this coil, under the coil which is undergoing the commutation, and for generating that EMF, what should be the flux density. This L is fixed, V is fixed. I have to control this B. Now B is controlled by this Ni, right? So if I change the number of turns such that the flux density under these poles, interpoles, is such that the EMF induced in this coil is equal and opposite to this, like this. Okay, so now you can actually think of how to design a core of a DC generator or a DC motor. What should be, if I want a 2000 kilovolt DC generator, then if I fix the length of the core and the speed of a core, then I will be left with the number of poles, right? I will be left with the type of winding. Then I will be left with how to choose the turns in a coil. Then what is the width of the core, width of the poles, how to choose the number of turns of the field winding, like that. So these all I can design based on these simple magnetic principles. Based on all these principles, I can design the various elements of the DC machine. Okay, so today's class we have discussed about how to mitigate the commutation problems, and those are manually shifting the brush positions, which is absolute and it has many drawbacks. Next one is interpole placements. Interpole placements will actually nullify the shift in magnetic neutral axis, but it will not eliminate the weakening of the flux or reduction or weakening of the flux. So that is why we go for third method, the compensating winding. So in compensating winding, armature reaction is completely eliminated, but it is also having some drawback, that is it cannot address the LDI by dt voltages. So that is why along with compensating winding we will be using interpoles, so that it addresses both problems, armature reaction as well as the LDI by dt voltages. And we have also seen some basic principles regarding the magnetic fields in the machine and how to come across fixing the various parameters in designing aspect. I'll stop here. Thank you.